Okay, welcome to Operating System CS332 class, Rutgers University, New Jersey. In these lectures, we're going to discuss the overview of a computer system, what consists of a computer system. And again, the main course is an operating system. So before we start with the operating systems, we will start with the computer system in general. So first, we will say that an operating system normally explores the hardware resources of one or more processes to provide a set of services to system users. So the operating system also manages the secondary memory, the input and output devices on behalf of its users. So here we can say that the main goal of an operating system is also to manage and control the computer hardware resources. Operating system also normally interacts. That's the only software that interacts with the computer hardware. So it manages, again, the computer hardware resources and also controls it. So it's very important to have some understanding of the underlying computer system hardware, again, before we begin our examination of operating system. So these lectures will provide an overview of computer system hardware. And in most cases, the survey is very briefly. And here we are assuming that students are very familiar with this subject. Again, what is a computer system? Most of us taking the introduction to computing already. And so we know what is an hardware, what is a software, the definitions. So again, we will not go in details. So here we can say the basic element of any computer system. At the top level, a computer consists of a processor, memory, input and output devices, and also the system bus. Normally, the system bus will connect all the computer resources, the hardware together. So a system bus is more or less like a wiring system or a conductor. So these components, again, are interconnected in some fashion to achieve the main function of the computer, which is, again, to execute programs. So operating system main goal always is to execute programs. And as we said, again, there are four major, or I would say the four basic elements of any computer system. Again, the process, I/O, which is the input and output devices, system bus, and also the main memory. So first we start with what is a processor. Again, and this course is about operating systems, so we will not go details about a processor, for example, the elements or the components of a processor. We know a processor has so many different parts. We may discuss the processor in abstract level, more general form. So here first we say a processor normally controls the operation of the computer and also perform its data processing functions. This is why we always say that the processor is the brain of the computer. Again, it controls the operation of the computer, and also, most important, it performs all the data processing, the decision-making, arithmetic operation, everything is done. So we refer to a processor as the central processing unit also. Next, we go to the main memory. So main memory is where normally our execution takes place at. So normally when we start our computer, the first thing that will be loaded to the main memory is our operating system, the kernel files. So the main memory, again, here we say it stores the data and programs. Any programs that need to be executed must first of all loaded into the main memory. At the moment, I'm using the PowerPoint slides. This PowerPoint slides is loaded into my main memory. So this memory is typically volatile. Volatile means when the computer is off, all the data in the memory will be lost. So the content of the memory is lost when the computer is shut down. Also, it's referred to as a real, again, memory or the primary memory. That's another term we use. Next, we talk about the I/O devices, or here we say the modules. Normally, the I/O modules move data between the computer and its external environment. So for example, an input device can be my keyboard. I will enter a data into the computer using the keyboard. I want to display my result that I got from the computer after finish execution. This result must go through an output device. So output device example will be the monitor or the printer or speaker. So that's why we say the I/O modules move data between computer and its external environment. The external environment can be both the input and output devices. So example here, we have the secondary memory devices. This is where data can be stored again, permanent. Example would be my hard drive of disk, such as flash drive, etc., or CD disk. Also communication equipment, and also the terminals. So the external environment consists of, again, different types of devices. Can be the secondary devices again. It can be a communication equipment such as a network interface card or any communication devices, for example, the modem. Also can be the terminals. Now, system bus, I would say a system bus is more or less a wiring system. So system bus connect all the computer hardwares together. For example, the CPU to memory, so data can flow, signals can flow between them. So here we say a system bus normally provide for communication, provide the communication among processors, the main memory, and also the input and output modules. So this is a very short example we have here. So we can say a typical computer system. These are all the devices. For example, the CPU, which is the central processing unit, or the processor. It has a lot of components by itself. For example, PC stands for the program counter, which normally point to the next instruction to be executed. Instruction register is like a memory in the CPU that holds the instruction temporarily. We also have the execution unit. We also have the I/O and BR. BR stands for, again, the buffer register. So a buffer also is another term for memory, special memory. We also have the I/O address register again. So again, as we said, this course is not a computer hardware course, it's an operating system. So we will not discuss detail about all these components. But in general, we should know a computer system consists of CPU, which have different components that works together to accomplish a goal. And also we have the I/O module, which here can be the input and output devices, etc. Then we of course have the main memory. This is the most important part, because for data to be executed, at least it must be stored in the main memory. So for example, I have a program or data stored in my hard drive. My hard drive is a secondary storage device, it's permanent. Now, if I want to execute or use the data for processing, I have to open that data or the file. When I open it, automatically it will be loaded to the main memory. This is done by our operating system. So our operating system, I would say, is the main coordinator between the user level and the hardware level. The next we talk about what is a microprocessor. So again, here we say this is an invention that brought about the desktop and the handheld computing. We know the term micro, again, means something that is very, very small. And micro means small. So previously, somewhere in the 50s, 60s, a computer can be as large as a regular size of a room regular size, very large. But with the invention of microprocessors, the size of a computer was able to be reduced. So here we say again, the hardware revolution, but that brought about desktop and also the handheld computing was the invention of the microprocessors, which contains a processor on a single chip. And though originally is much slower than the multi-chip processors, but microprocessors again have a very unique features in the sense that again, very, very small. It make it possible to reduce again the size of our computer that leads to desktop, laptop, etc. And now microprocessors have continually evolved to a point that they are now much faster for most computations. Again, due to the physics involved in moving information around in, again, sub-nanosecond time frame. So the next is our graphical processing unit. So a graphical processing unit is also a central processing unit, but it's more, again, powerful. So here it provides efficient computation on arrays of data using a single instruction, multiple data techniques, pioneers in the supercomputers. So it's more faster again than our conventional central processing units. So here, although the processors provide a very good performance, for most forms of computing, but there's increasing demand for more powerful, high computation, very complex computation, such as graphic and video games, which demand more. The size is very big, demand high performance. So graphical processing unit provide efficient computation for that. So no longer used just for rendering advanced graphics. They are also used for, again, for example, here physics simulation for games, computation on large spreadsheets, especially high performance algorithms, very complex algorithms. We also have the digital signal processes. Normally this deal with streaming the signals, such as audio or video. So digital signal processes are also present for dealing with streaming signals, as we said, such as audio and again, videos. And they are used to be embedded in input and output devices. Example will be the modems, but they are also now becoming first-class computational devices, especially in handheld devices, such as tablets and cell phones, etc. Now we have what we call the system on a chip, which is SoC. This normally satisfies the requirement of a handheld devices. And the classic microprocessor is giving away to, again, system on a chip. So to satisfy the requirement of a handheld devices, the classical microprocessor is again giving way to the system on a chip, where not just the CPU and caches are on the same chip, but also many of the other components of the system, such as the DSPs or GPUs or the I/O devices and the main memory. So that's where other components on the system, such as again DSP, GPUs, that's the graphical processing units, the input and output devices, etc. So the next is the instructions execution. So here we say there's two steps. A program consists of a set of instructions stored in the memory. So for the instruction to be executed, first thing, it must be fetched. So processors read or fetches the instruction from the main memory or the memory in general. Then after it fetches it, the processor will execute each instruction. Normally, to go through at least, again here, we are not doing, this is not a hardware classes, so we don't go details about all these things, just to get a general idea. But normally when the instruction is fetched from the memory, it needs to be decoded before executed. And there's a process of doing that, which we are not going to discuss much here. The only thing we should know here is that the processor always reads or fetches instruction always from memory area. It can be a cache or a register from main memory, and then execute each instruction. So program execution consists of repeating the process of instruction fetch and then instruction execution. Instructions execution may involve several operations and also depends on the nature of the instruction. So this is a diagram, give us the idea. So there's a start. When we start, the first thing we do, we need to fetch the next instruction. Then we execute the instruction. If we complete, we are going to halt it. Other than that, if we haven't finished the execution of the program, then we have to go back again, fetch the next instruction, execute, fetch the next instruction, execute, until if we complete, then we halt. So instruction, fetch, and execute. Here we say the processor normally will fetches an instruction from main memory or the memory. And typically the program counter points to the next instruction to be fetched. So program counter is incremented after each fetch. And we also have the instruction register. So instruction register, normally here we say fetch instruction is loaded into the instruction register. So the term register again is a special memory, either in the CPU or very, very close to the CPU. An instruction register normally will hold the instructions that was fetched from the memory. So the processor will interpret the instruction and perform required action. Example, processor memory or processor IO, data processing, and controls. So at the beginning of each instruction cycle, the processor normally will fetches an instruction from memory. Then typically the program counter holds the address of the next instruction to be fetched. Unless instructed otherwise, the processor always increments the program counter after each instruction fetch so that it will fetch the next instruction in sequence. So instruction located at the next higher level address will be pointed. So for example, consider a simplified computer in which each instruction occupies again one 16-bit word of memory. Now, assuming the program counter is set to 300, then the processor will fetch the next instruction at 300. On succeeding the instruction, again, it will move to location of 301, 302, 302. So after each instruction, 300 is finished, point to the next one, and this sequence may be altered as needed. It depends on the program. So that's the whole idea here. Here we have again a memory. We have the address section for the instruction format. So PC is the program counter, holds the address of the instruction, and the instruction register, so instruction be executed, hold the instruction that is being executed. Memory have all the instructions. Program counter point to the next instruction to be executed. Then the register will hold the current instruction that is being executed. Also, we have the accumulator AC, which is also a temporary storage place. So the fetch instruction is loaded into the instruction register. The instruction again contains bits that specify the action that processor is to take. Then the processor interprets the instruction and perform the required action. In general, these actions fall into 4 categories. Again, 4 categories. So we have the processor memory. Data may be transferred from processor to memory or from memory to processor. We also have the processor I/O. Then in this case, data may transfer to and from any I/O devices to the processor and back again. Then data processing, again, the processor may perform, example would be the arithmetic or logic operations. Logic operations is based on decision making, either is true or false decisions. So the figure here again gives us some partial program execution. So we can see the fetch stage on the left column. We have the write is execution stage. So let's say we have a memory at 300, as we said before. These are the memory addresses, 300, 301, 302. The content inside is the instruction that need to be executed. So we can see that the first instruction, that this is our memory address. So we start from the top 300. That will be the current instruction that need to be executed. So we can see that the instruction will be loaded into the CPU register. Here we can say, again, this is instruction. So we can say the instruction register, which is IR. Then we have the AC. Then we have the program counter normally point to the next instruction to be executed, which is 300. After 1940 is executed, the program counter will turn to 301 because that will be the next address. Then that will be executed. So that's what we see here. You can see that the program counter now is 301, and that is the instruction that need to be executed. The instruction need to be executed is 5941, which is owned by the instruction register. And this process keeps going throughout. So that will be the conclusion of our first Unit 1, Part 1 lectures, which cover Chapter 1, Section 1 and 2. The goal here is to get a concept of, again, how a computer system is organized. So again, wish everyone the best. Thank you.